We're now going to solve an example problem using the log mean temperature difference approach. And for this problem, we're looking at a feed water heater. And what I'm going to do, I'm going to begin just by writing out what is known. I'm not going to write out the problem statement. So we know that we have a feed water heater. We're told that it's a shell and tube heat exchanger, and we're given information for both the shell and the tube. So for the shell side, we're told that it is a one pass, and the fluid going through on the shell side is condensing steam with a saturation temperature of 120 degrees C. And then for the tube, the other thing that we're given the overall heat transfer coefficient. And we're told to find, we're looking for the area of the heat exchanger that would correspond to that overall heat transfer coefficient. So when you look at this, we know a number of things. We know the inlet temperature on the tube side, so this is the cold fluid. We know the exit temperature. We know the inlet and exit on the shell side, so that's our hot fluid because it's going through a condensation process, so the temperature will remain at 120 degrees C. So those are all the elements that we said that we need in order to apply the log mean temperature difference. So let's go ahead and use the analysis for LMTD. So we're going to use LMTD. Now note that this is not a double pipe heat exchanger. So what we're going to do, remember I told you that there are correction factors that exist when you're dealing with heat exchangers that are not double pipe. So what we're going to do, we're going to model it as a counterflow double pipe unit with the correction factor F that we'll get from a figure. I won't give you the figures, but I'll show you essentially what would be in the figure, and you can find these in textbooks. The equation that we're going to use here is going to be the following. Where delta Tm is our log mean temperature difference. So what we're going to do, we're going to begin by sketching out the temperature distribution. Remember I said that that can quite often help you when you're solving these problems in order to understand what is going on. Okay, so we have our two fluid streams in the heat exchanger as shown. Now, what I'm going to do, I'm going to label these in order to apply the LMTD. First of all, this here is temperature hot at 1, and this is temperature hot at 2. This is temperature cold at 1. This is temperature cold at 2. So what I'm doing is assuming that that's location 1 and that's location 2. With that, we can calculate the log mean temperature difference. And the other thing that I am going to do is when we're trying to determine the F factor that we have for LMTD, given that this is a shell and tube exchanger and not a double pipe, there are other symbols, and I'll show you a schematic in a moment that will help make sense in terms of where I'm getting these symbols from. But essentially, these are the fluid streams that will then enable us to determine that F factor. Or these are the temperatures for the fluid streams, I should say. Okay, so notice we have this, 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 and this. Those all lead to the F factor. Now, the equations that we have here, we're going to begin by determining the amount of heat transfer by looking at the cold fluid. So this here is the cold fluid. And this up here would be the hot fluid. And it is condensing, and consequently it is not changing temperature as it goes through. But what we can do, we can write out Q, and this is going to be the heat exchange, is the mass flow rate of water times the specific heat of water. And the water was the cold fluid, but I'll just put water. And then TC1 minus TC2. So that's taking the hot temperature minus the cooler temperature. Now, in this, what we need to do, we need to be careful about this because the specific heat of water or of any fluid is a function of temperature. And consequently, what we need to do is we need to be able to obtain that at the average temperature. So average water temperature with that we get CP 4182.6 joules per kilogram Kelvin. Now I did say CP is a function of temperature for all fluids. I should make a disclaimer there because if you look in thermodynamics, helium, the CP value is a constant. It is not a function of temperature. And I think it's for all of the other gases that are in that column in the periodic table. It turns out that the CP is not, it does not change with temperature. But anyways, that's just an aside. So we're dealing with this. We have the value of CP for water, and that's at the average. So with that, we can calculate the heat transfer. So we know the mass flow rate of water was 2.5 kilograms per second. Be careful when you're pulling the values out of the back of the book or wherever you're getting them from. Sometimes they're in kilojoules per kilogram Kelvin, and so you have to be careful to put that in joules. And then we have 100 minus 30. We end up with then 731.96 kilowatts is the heat exchange. Now, that is giving us the heat transfer. We want to determine the area. So what we need to do next is determine the log mean temperature difference. So let's do that next. So if we go back and look at our temperature diagram, what I'm doing here is doing basically the first one is T hot 2 minus T cold 2. So it's this differential. And then the other differential that we're going to be evaluating is that one there. So that's what we're doing here. And dividing by the logarithm. And remember I said that the numerator was just going to be the first term that we have here. So it's this one. And then the denominator is this one. And with that we get delta Tm, or the log mean temperature difference, is 46.54 degrees C. Okay, so we're almost there. We have Q is UAF delta Tm. And what we have thus far, we've determined that. U was known. We're looking for area. We just solved for that. We still need to get this F factor. And that is the correction factor for the fact that this is not a double pipe heat exchanger. It's a shell and tube heat exchanger. And this is where we're going to pull those different temperature values that I was showing you when we looked at the temperature diagram. And for that, I'm going to draw a little schematic. And this is going to vary from book to book. But the one that I have as a reference, they label the temperature of the shell or of the tube fluid stream. So this is going through and there's a loop, and then they show that there are baffles here. And then they show the tube inlet coming here with capital T, or sorry, that's the shell inlet, and the shell exit, capital T2. So with those, you can then, just by looking at the schematic and reading the problem statement, you can figure out which is the big T and which is the little t in the temperatures. And then what you would do, there would be another chart, and in this other chart what we would have is the correction factor, and that would be plotted against some variable P that I'll define in a moment. And then there's going to be a number of different curves, and these curves are going to be for different values of R, yet another factor that we'll define in a moment. So R is defined in the following manner, and P is defined in the following manner. And this would depend upon the figure that you're using for the particular heat exchanger. So you have to be a little careful with that. But what you would do is you go back to your temperature diagram. So let's do that. And let's begin. And what we're going to find out, T1 minus T2. So going back to our temperature diagram, T1 is here, is 120, and T2 is there. It's also 120. So let's look at our equation here. This here is going to be 120 minus 120, which is 0. So we're going to get an R value of 0. And there is no curve for 0. So you're going to wonder what's going on. Well, it turns out that this is a unit with a phase change. And whenever you have a phase change, so either condensation or boiling with one of the streams, then we can just make the assumption that F is equal to 1.0. Okay, and so with that, now that we know F, we know Q, we know delta Tm, it's pretty straightforward then to evaluate the area. So there we go. We get 7.864 square meters. This would be known as a sizing problem. You know your fluid streams and you're determining the size of the exchanger that is required. So that's a case of LMTD. It seemed to work quite well. What we'll do in the next segment is we're going to solve the problem again using LMTD where things don't work quite as well, and that will lead us to a new approach for being able to solve heat exchanger problems.